Okay, let's unpack this. Picture this. You're chilling at a park, maybe, and a friendly humanoid robot walks towards you, carefully balancing a full cup of beer.
Uh-huh.
It gets right up to you, smoothly extends its arm, and hands it over, and doesn't spill a single drop.
Yeah, that sounds like something we just kind of expect a robot should be able to do, right? It feels simple.
It feels simple to us, exactly. But for the robots we have today, even that straightforward task, it's actually incredibly difficult.
It really is. It highlights this big challenge.
Yeah, we're seeing humanoids get amazing at walking, climbing stairs, even dancing, on tricky ground.
Yeah.
Their locomotion is getting really
The
good.
walking part, yeah. Fast advances there.
But trying to do something precise, something delicate with their hands, their end effectors while they're moving, that's still a major hurdle.
A huge one. And it's not just about, spill-free beer delivery, fun as that sounds.
Right. It's crucial for any kind of safe, reliable interaction in our world, like handing you a fragile tool or maybe doing some detailed work or
Or even just holding a video camera steady while it walks around. That stability is key.
absolutely. That gap in performance, it's a real bottleneck for making these humanoids genuinely useful companions or workers in our messy, unpredictable human spaces.
Totally. Which brings us to our source material for this deep dive.
Exactly. We're looking at a research paper called Hold My Beer, Learning Gentle Humanoid Locomotion and End-effector Stabilization Control. It's by Yitang Li and colleagues from Carnegie Mellon University and some affiliated interns.
Great title, by the way.
Isn't it? It perfectly captures the challenge. So we're going to dive into their research, really understand the specific problem they were aiming to solve, and explore the framework they came up with.
And their solution has this, well, memorable name. So SoFTA stands for Slow Fast Two-Agent Framework.
SoFTA. Okay.
And honestly, the name gives you a pretty big hint about their core idea. They decided to tackle this really hard problem by, well, splitting it up.
Right. So our mission today is to dig into this paper, understand the SoFTA framework, see what their experiments, both in simulation and the real world, actually revealed.
And figure out what this tells us about building humanoids that can move confidently and act with precision. What are the absolute key nuggets you need to know from this specific research?
Okay, so where do we start? Why is it so hard to keep a hand steady while walking?
So the researchers, they really pinpointed that the difficulty boils down to a fundamental mismatch. A mismatch between what walking needs and what keeping a hand steady needs.
A mismatch. Okay, walk us through that. What kind of mismatch?
Well, there are actually two key mismatches they identified. First, there is a mismatch in the task objectives themselves.
Okay.
Locomotion, walking, it often involves momentum, right?
Right.
You lean into a step, the robot isn't perfectly static. It's
Yeah.
handling these non-quasi-static dynamics. It needs to move.
Makes sense.
But stabilizing an end effector, the hand, for a delicate task, that demands the robot's base be as still and controlled as possible. You need precision. So those objectives are kind of pulling in opposite directions.
Okay. One wants dynamic movement, the other wants almost perfect stillness. I get that. What was the second mismatch?
The second one is in the dynamics of the robot's own body, how its different parts naturally move and how they're controlled.
Right.
The lower body, the legs, they operate with what the researchers describe as slow dynamics. Control comes from discrete foot contacts, weight shifts. It happens over relatively larger timescales, tied to the whole gait cycle.
And it needs to be robust, right? Because of the real world being messy.
Exactly. Locomotion is highly sensitive to that sim-to-real gap, those unavoidable differences between a nice, clean simulation and the messy real world. So lower body control needs to be super robust.
Okay, so that's the slow part. What about the arms, the upper body?
That's where the fast dynamics come in. Arms, they typically have fully actuated joints. You can apply torque continuously, rapidly.
Much faster control.
Way faster. You can make fine, quick corrections much more easily with an arm than you can by, say, trying to adjust the robot's entire balance just through its feet.
Okay, wow. So we've got slow, discrete, robust control needed for the legs versus fast, continuous, precise control possible with the arms. And the tasks they need to do conflict.
Yeah, no wonder a single controller trying to juggle all that would struggle.
Exactly. And the paper uses this really striking example to illustrate just how bad it can be. They looked at the default controller on a standard robot, the Unitree G1,
Okay.
just having the robot tap its feet in place like a simple stepping motion.
Yeah.
That robot showed average end-effector accelerations around 5 meters per second squared. 5.
5 meters per second squared. That sounds high, but like, what does that compare to? Say, a human trying to hold their hands steady. Is that a lot?
It's huge. It's over 10 times higher than typical human levels of stability doing a similar kind of task.
10 times. Wow. Yeah. Imagine trying to hold a full cup with your hands shaking and accelerating that much. You'd have no chance. Spills everywhere. It'd be impossible to do anything delicate. That number really drives home the scale of the problem they were tackling.
Okay, yeah, that comparison makes it crystal clear. So, this SoFTA framework, their slow, fast, two-agent approach, how does it propose to handle this fundamental difficulty, these mismatches?
Well, the core insight, the clever part, is that instead of having one single monolithic control system trying to wrestle with all these conflicting goals and dynamics,
Okay.
they decoupled.
The decoupled, split it up.
Exactly. They used reinforcement learning, RL, to train two separate agents, each one specializing in a different part of the problem, a different part of the robot.
Two agents, okay, each with a specific role.
Precisely. Agent 1 is the lower body agent. It controls the robot's legs and the waist that's 13 degrees of freedom in this case.
Right.
And crucially, this agent operates at a lower frequency. They use 50 hertz. Its main job is robust locomotion, keeping the robot balanced, working on that slower time scale of the gait cycle.
50 hertz for the legs and waist. Got it. And agent 2?
That's the upper body agent. It controls the arms, 14 degrees of freedom. And this one runs at a higher frequency, 100 hertz.
Double the speed.
Yep. Its priority is that rapid, precise end-effector control, compensating for any movement coming from the base, making those fast, continuous adjustments we talked about.
Okay, so they're splitting the robot's body control and the control speed. What's the big advantage? Why do it this way?
Well, the decoupling, it offers several major benefits. First, by giving each agent its own sort of action space and value space, you let them become experts, right?
Specialize.
Exactly. The lower body agent masters the tricky stuff like foot contacts, balance, dealing with the ground, while the upper body agent focuses purely on minimizing that hand acceleration.
And the different frequencies, you said 50 hertz and 100 hertz, that feels very deliberate.
Oh, it is. It's strategic. Like we discussed, the tasks just have different natural speeds. Trying to control the lower body at a really high frequency, say 100 hertz, it sounds good in theory, maybe more reactive.
Yeah, you'd think faster is better.
But in practice, it actually makes the lower body more sensitive to real-world noise and delays. They found it made locomotion less stable, prone to oscillations in real tests.
Ah, okay. So faster isn't always better for the legs.
Not in the real world, it seems. Conversely, running the upper body at a lower frequency, like 50 hertz, just wouldn't be fast enough to react effectively to sudden disturbances or the subtle movements from the base.
So the slow, lower, fast upper combo, it's about matching the control rate to the specific dynamics and needs of that part of the robot.
Precisely. Matching the speed to the task and the hardware reality.
That makes a lot of sense. What about how they learn? You mentioned reinforcement learning. That usually involves rewards, right? Giving the AI positive feedback.
Right, and this is another clever part of the decoupling. Because the goals are so different, robust walking needs rewards that look at longer periods, completing stable steps.
Right, success over time.
Whereas EE stabilization needs sharp, immediate rewards, like, is the hand shaking right now? Penalize that instantly.
Very different reward structures needed.
Totally. So they gave the agents separate reward groups. This stops them from getting in each other's way during training. If you had one single agent trying to optimize both, well, prioritizing minimal hand wobble might make the robot take really weird, unstable steps.
Or vice versa. Focusing on a smooth walk might let the hand bounce all over the place.
Exactly. Separating the rewards gives each agent clearer, more targeted feedback. It helps them learn their specific job much more efficiently without confusing signals. They do share one thing, though.
What's that?
The termination reward. If the robot falls over, both agents fail together. That encourages overall task success.
Okay, so separate goals, separate rewards mostly, but shared failure. Makes sense. But they still need to work together, don't they? The upper body kind of needs to know what the lower body is doing to compensate properly.
Absolutely. And that's handled because even though they have separate control networks making the decisions, both agents get the same full body observation.
They both see everything.
Yeah, they both get information about all the joints, the robot's orientation, its velocity, forces, everything. This shared information allows them to implicitly coordinate their actions, even with their separate goals and frequencies. The upper body can see the base moving and react.
All right, the theory sounds really solid. Divide and conquer, match the speed to the dynamics, give focused rewards but shared info. But the proof is in the pudding, right? How did SoFTA actually perform when they tested it?
They put it through some pretty rigorous testing, starting, as usual, in simulation.
Safer place to start.
Definitely. They designed scenarios like just tapping in place, making the robot follow RAND command random motions, and reacting to push scenarios where they simulated external disturbances.
Okay. And how did it stack up against other methods? What were the baselines?
They compared SoFTA to a couple of main baselines. One used reinforcement learning, RL, for the lower body, similar to SoFTA's lower agent, but then relied on traditional inverse kinematics, IK, to calculate the arm movements needed for stabilization.
So RL legs, classic math for the arms.
Kind of, yeah. The other baseline was a single RL agent trying to control the whole body at once. One brain trying to do everything.
The monolithic approach, got it. And the results in simulation.
SoFTA consistently outperformed both baselines. It showed significantly, quote, superior EE stability, especially when dealing with those disturbances like the push scenario. It dramatically reduced those end-effector accelerations we talked about earlier.
So clear win in sim.
Yeah, it was strong evidence that the two-agent decoupled approach, this slow-fast idea, worked really well, at least in that controlled virtual environment.
Okay, simulation is one thing. We know that. Getting robots to perform just as well in the real messy world, that's often the biggest challenge. How did SoFTA do on actual physical robots?
That's the critical step, absolutely. And they did deploy it. They put SoFTA onto the Unitree G1 robot, the same one they used to show the initial problem with the shaky hand.
Right, the 5-meter swan one.
That's the one. And they also tested it on another humanoid called the Booster T1. For these real-world tests, they compared SoFTA mainly to the robot's default, built-in controller.
The shaky one.
Yep. And also against that whole-body RL baseline, the single agent trying to do everything. They left out the IK baseline here.
Why?
Probably because IK methods often rely heavily on having perfect state information, which is much harder to get reliably in the real world with sensor noise and slight inaccuracies. It's generally less robust.
Makes sense. So what kind of real-world tasks did they run similar to the simulation?
Pretty similar, yeah. They tested basic tapping in place, having the robot walk along a line, tried track, and doing turning motions in place.
And the outcome in reality? Did SoFTA hold up?
It did. The robot's default controller was, well, as expected, the worst for stability. Shaky. The whole body RL baseline was better than the default, but they noted it struggled with the more dynamic tasks, like following the trajectory smoothly.
Okay. And
SoFTA, according to the paper, showed consistent and robust performance across all these real-world motions. It managed to keep the end effector much steadier even during these varied dynamic movements.
That's impressive. Holding up against the unpredictability and noise of the real world is a big deal.
It really is. And they specifically noted that SoFTA seemed to have better sim-to-real transferability compared to that whole-body RL approach.
Meaning it worked better in reality than the simulation predicted compared to the other method.
Or rather, the performance drop from sim to real was less severe. They observed the whole-body RL agent took, quote, sluggish and hesitant steps in the real tests. It suggests that its strategy, trying to control everything together, didn't transfer cleanly from the perfect simulation to physical reality.
Huh. That's really interesting. So the decoupled approach didn't just help the agents learn specialized skills, it also seemed to help them adapt better when they were actually put onto a physical robot.
That seems to be the case. The separation might make each agent's task simpler and thus more robust to real-world variations.
Did they uncover anything specific during the training process that helped with this real-world transfer? Any particular trick?
Yes, actually. They highlighted a key detail in how they trained the upper body agent. Initially, you might think you'd train it to keep the hand stable at one fixed position in space.
Yeah, seems logical. Hold it right here.
But they found that wasn't as effective for real-world performance as training it to stabilize the end effector at random target positions relative to the robot's body.
Random positions. Why would that be better?
The thinking is, training with random target positions forced the upper body agent to learn more general, reactive compensation behaviors. It had to learn how to stabilize no matter where the hand was supposed to be relative to the moving base. This made it much more adaptable when the robot's base was moving around somewhat unpredictably in the real world.
Ah, I see. So it learned a more general skill of stabilizing rather than just holding one specific pose. That makes it more versatile for unexpected movements.
Exactly. And you really see the tangible results of this robustness, this stability, in the capabilities it actually enabled on the physical robots. The demos.
Like the beer test we started with? Or, well, the non-alcoholic version.
Pretty much. They use bottles of water or maybe soda for safety, understandably.
Hmm.
But yes, in the videos they show, without soft eyes stabilization active, the liquid in the cup sloshes around dramatically. Even minor foot impacts cause big waves.
Yeah, I can picture that.
But then they turn SoFTA on, and the liquid motion is hugely suppressed. It allows the robot to carry a nearly full cup while walking quite normally.
That visual proof is really compelling, isn't it? It's one thing to see numbers and graphs, but seeing the liquid stay relatively still, that hits differently.
It absolutely does.
Mhm.
And they didn't just show walking, they demonstrated its ability to handle disturbances too. They actually gave the robot sudden and forceful pushes while it was carrying the cup.
Pushed it while carrying liquid. Brave.
Right. And what happened was the lower body agent would adjust the robot's gait, maybe take a wider step or shift its weight, to stay upright and balanced,
While the upper body,
while the upper body agent actively compensated for that disturbance and the lower body's reaction, keeping the end effector, the cup, remarkably stable, preventing spills even during the push recovery.
wow. Okay, so the two agents really are coordinating effectively in the real world. One focuses on not falling over, the other focuses on keeping the hand steady, and they manage to do both simultaneously, even under pressure.
Precisely. That's the emergent behavior you want to see. They also showed another cool application, using the robot as a mobile camera stabilizer.
Ah, like a walking gimbal.
Kinda, yeah. When the robot turned continuously without SoFTA stabilization, the video footage recorded from its hand was visibly shaky, jittery.
As you'd expect from the earlier numbers.
Right. But with SoFTA enabled, the exact same turning motion resulted in smooth video footage. It effectively turned the robot into a stable platform for sensors or cameras, even while moving.
That has huge implications for inspection, surveillance, telepresence, lots of applications.
Definitely. Okay, so SoFTA clearly delivers impressive results on the stabilization front. Let's circle back quickly to that slow-fast frequency design. That specific 50 hertz lower, 100 hertz upper split. Was that just like their first guess, or did they test other combinations?
Good question. Did they experiment with the speeds?
They did. They ran a detailed analysis on this very point. They experimented with different combinations of control frequencies for the lower and upper body agents.
Yeah.
They tried 33.3 hertz, 50 hertz, and 100 hertz for both parts of the body.
Okay, so they tested slower and faster options for both. And did their initial slow-fast design 50 lower, 100 upper actually prove to be the best?
According to their experiments, yes. That specific combination consistently performed best across the various tasks and environments they tested, both in simulation and, importantly, on the real robots.
Interesting. What did the analysis tell them about why that particular combo worked best? What was the reasoning?
Well, the analysis reinforced what we suspected earlier. It showed that a 50 hertz frequency for the lower body was perfectly sufficient for stable walking in simulation. But crucially, it was significantly more robust to real-world issues, things like sensor noise, communication delays between the computer and the motors.
The stuff that messes up sim-to-real transfer.
Exactly. Compared to running the lower body at 100 hertz. They actually found that trying to control the legs that fast in real tests often led to oscillations, instability, and even failures.
Fascinating. So pushing the lower body to be faster actually backfired and made it less stable in reality.
That's what the results indicated. But for the upper body, that higher frequency, the 100 hertz, was beneficial.
Why there?
It allowed for much faster reaction and recovery during sudden events, like when the robot stopped abruptly or when it received one of those pushes. The faster upper body control resulted in quicker response times and lower peak errors in the end effector position. It could correct faster.
So it really reinforces that idea of strategically matching the control speed to the specific requirements and, maybe more importantly, the physical constraints and realities of each part of the robot's dynamics. 50 for robust legs, 100 for nimble arms.
Couldn't have put it better myself. And they even took it one step further to check if this whole approach was just specific to the Unitree G1 robot.
Ah, they tested it on another robot.
Yes, they did what they call cross-embodiment validation on that booster T1 robot we mentioned earlier.
Which is physically different.
Yeah, different joint configurations, different body proportions. Despite these physical differences, applying the same SoFTA training framework, the same principles resulted in significantly better stability and coordination on the booster T1 compared to its own default controller.
That's really important. It suggests the design principles of SoFTA, that slow-fast split, the two-agent decoupling, the separate rewards, the strategic frequencies, aren't just a fluke tuned for one robot model. They seem to be fundamentally sound and transferable.
Exactly. It's a strong sign that the core approach has potentially much wider applicability across different humanoid platforms.
Okay, this all sounds very positive, but, any good research paper, any honest assessment also needs to point out its own limitations. What did the authors themselves identify as areas where SoFTA still falls short or maybe needs more work?
They were quite clear about this, which is always good to see. First, they readily acknowledged that while the stability is vastly improved, like really significantly better,
Yeah.
it's still not perfect. It's not yet at a truly human level of effortlessness. Like us carrying a full water cup without even consciously thinking about the micro adjustments we're making.
Right. So a big step forward, impressive, but still room to grow to reach that seamless human dexterity.
Exactly. Second, they note that while the decoupling is very effective for many tasks like the ones they tested, it does create a fairly fixed boundary between the lower and upper body control systems.
A hard split.
Yeah. And this rigid separation might actually be less optimal for tasks that require very close, dynamic, and highly integrated coordination between the upper and lower body.
Like what kind of tasks?
Think about something like a really dynamic reaching motion where the robot has to lean way over, adjust its footing, and use its whole body fluidly and simultaneously to grab something far away. The current fixed split might struggle there.
Okay, so acknowledging that the very division of labor that makes it work well for stabilization might become a limitation for certain kinds of truly complex whole body manipulation.
Potentially, yes. And finally, kind of related to that, they mentioned that the performance might still have some variability. It could depend on the specific complexity of a new, untested task, or the exact morphology, the body shape and mechanics of a different robot, or if a task just requires more nuanced, integrated coordination than the current decoupled framework inherently provides.
Right, so still some unknowns about how it generalizes to all possible tasks in robots.
Okay, so to kind of wrap this up then, so ATA, this slow, fast two-agent framework, it's a really novel approach tackling that tough problem, keeping a humanoid robot's hands stable
Right.
while it's walking around.
Yeah, and it achieves a really significant improvement. We're talking reducing those end-effector accelerations by, what, 50, 80% in many cases, bringing stability much closer to human levels.
Which unlocks those capabilities we saw carrying liquid without major spills, acting as a stable mobile camera platform, things that were really hard before.
And the core insight, the key mechanism, is that clever decoupling. Splitting control between a slow, robust lower body agent running at 50 hertz, focused on walking.
And a fast, precise upper body agent at 100 hertz focused just on stabilization.
Right. Each running at strategic frequencies, trained with targeted rewards, but sharing all the sensory information so they can still coordinate their actions implicitly. This feels like a really crucial step, doesn't it, towards building humanoids that can interact with our world in more practical, reliable, and dare I say, gentle ways. It really moves the needle on physical dexterity while the robot is mobile.
Absolutely.
Hmm.
It brings us genuinely closer to robots that can navigate and manipulate safely and effectively in busy, unpredictable human environments.
Well,
Less like clumsy machines, more like capable helpers.
yeah. It makes you wonder, though, building on those limitations they mentioned, if this decoupled approach works so well for many tasks precisely because it simplifies things, splits the problem, when will we really hit a wall? When will we absolutely need a more integrated, maybe more complex, dynamic, whole body control approach for the next level of tasks?
That's a great question. Where does decoupling become a hindrance rather than a help?
Right. Or thinking about the gap that still exists to truly human level, effortless stability. What kind of next breakthrough might be needed? Is it a different AI learning architecture? Maybe some way to dynamically blend decoupled and integrated control depending on the task? What do you think is needed to achieve truly human level dexterity and robustness in robot manipulation while they're moving around? What stands out to you from this deep dive as the biggest question or the next big challenge this work points towards?